All right. So, what do you think will happen if a patient receives too little anesthesia? Yeah, they might wake up during surgery, or too much. What do you think? They could die. They could have a hard time waking up. All right, and then for number two, what did you guys notice about the graph? Anybody notice?
The less the concentration of anesthesia, the longer the time is. Like after it reaches 7, it starts going down.
Right.
The less the anesthesia.
So it kind of increases super fast, and then it reaches a maximum, and then it starts going down. Did anybody wonder anything about the graph? What?
Why it does that?
Why? I don't know. All right. What would you guys estimate the concentration of anesthesia is after half an hour? It looks like about 3%. If you actually plugged it in, which I did, you plug in 0.5 for T, you get 2.8%. So either one is fine. All right. The anesthesia is effective once the concentration reaches 5%. So how long should the surgeon wait? 1 hour. And it says, how do you know? Well, you can tell. After 1 hour, the C of T reaches 5%. Right, and then how long is the drug effective? For how many hours? 5 hours. So between 1 and 6 hours. So from the graph, you can tell like that is where the concentration is at 5% or above. But it also tells you to do it algebraically. So to do it algebraically, you would put 5 in for C of T, and then you would solve it for T by multiplying 5 by the T squared plus 6. Right, and then that gives you a quadratic equation that will factor. So we're going to get everything on one side. What's wrong?
Oh, did you just multiply?
I multiply by the denominator. All right, and I'm going to divide through by 5. All right, so we end up getting the same T values that we got from the table. And then between 1 and 6 hours is a 5-hour time span. Yes, ma'am?
Well, for like future reference, do we have to do it like that? Because what I did, I put in 5 for T, and I still got 5 hours.
Well, when you plugged in 5 for T, you should have gotten whatever is here. So between 5 and 6 hours. So 5 in this case is not a time, so that shouldn't have worked. 5 is a concentration. So I don't know what happened there. You get like 5 point something if you plugged 5 in for T. So 5 needs to go in for C. All right. And then what do you guys anticipate would happen after many hours to the concentration of anesthesia in the bloodstream? It should level off. It should go away. We're going to say level off at 0. Now this algebraic function, after time, it actually doesn't ever get to 0. I do think in real life, eventually your blood will filter out the anesthesia. I don't know. Maybe there's some tiny bit of remnants of anesthesia in your blood after lots and lots of time. I don't really know what that works, how that works. But mathematically, algebraically, it actually is only 0 at one time. Do you guys know when that is? What? The very beginning, before they fit it into your blood. So we could do the same thing algebraically like we did up here at 4. We would set it equal to 0. 0 is, in this case, the concentration. And then when we multiply 0 by the denominator, it gives you 0. And then when you solve, you get that t is 0. So before the drug is administered. All right. So we're going to do the back together. So that's just kind of the introduction. So now we're going to start finding some things about rational functions. The 3 things we're going to find today are horizontal asymptotes, slant asymptotes, and Y-intercepts. There are, I think, 3 or 4 other things that we're going to find later. So we're kind of dividing it up. But there are tons and tons of characteristics of rational functions. So first, you need to know what a rational function is. So rational functions have the form f of x equals n of x over d of x. Why do you think I chose n and d? Numerator and denominator. So every time on this lesson, I'm talking about n, I'm talking about the numerator. And when I'm talking about d, I'm talking about the denominator. Now those 2 numerator and denominator functions are polynomials. So that's why this lesson is usually taught like right after polynomials. It's actually in the same unit in the textbook as polynomials because we use polynomial numerator and polynomial denominator. All right, so I realized that in these notes, I put how to find the horizontal asymptote before I told you what it was. So that's probably not a great idea. So we're going to squeeze in what a horizontal asymptote is. Now, you haven't learned about rational functions, but you have learned about functions that have horizontal asymptotes. So in Algebra 2, you learned about exponential graphs. Do you guys remember those? They have horizontal asymptotes. Do you remember what a horizontal asymptote is?
Where it like breaks off on like going left and right.
Right. It was where it levels off. So it's going to be a horizontal line. So let's write this down. A horizontal asymptote is a horizontal line the graph approaches as x approaches positive or negative infinity. And then that x approaches positive and negative infinity is just kind of a fancy way of saying the far left or far right of the graph. So as you go out away from the origin, the graph will get closer and closer to the horizontal asymptote. Okay. And so to find it, we're going to compare the degrees of the numerator and the denominator. So the largest exponents on the numerator and the denominator. So there's 3 things that could happen if you are comparing the degrees of 2 things, the numerator and denominator. It's possible that then their degrees are equal. The numerator's degree equals the denominator's degree. And when that happens, to get the horizontal asymptote, you're going to do y equals, and then in this case, we're going to make a long fraction. When you're actually doing it, it's a short fraction. We just have to write words here. So it's going to be y equals the leading coefficient of the numerator, which we'll say n, divided by the leading coefficient of the denominator, which we'll call d. And that is the horizontal asymptote. And a horizontal asymptote will always be the equation of a horizontal line. So it's going to be y equals a number. Okay. Another thing that could happen when you're comparing the degrees of the numerator and denominator is that the numerator is less than the denominator. And when that happens, y equals 0 is the horizontal asymptote. Okay? It doesn't matter what any of the other numbers are. You just look at the degrees. If the numerator is less than the denominator degree, automatically y equals 0. Right? And then the last case, when the numerator's degree is greater than the denominator's degree, then there is none. No horizontal asymptote. Okay, so I'm going to wait. Yeah, I'm going to wait right there and do some horizontal asymptotes, and then we'll come back and talk about the other things. All right, so for example 1, we're going to find 3 things, but right now we're just going to do a horizontal asymptote. Okay, so when we're doing the horizontal asymptote, finding it, we look at the degree of the numerator and compare it to the degree of the denominator. In this case, the degrees are the same. All right, so what we'll do now is that first part of the table. So we're going to do the leading coefficient of the numerator divided by the leading coefficient of the denominator. So that's going to be y equals 3 over 2. So that's just what you do for the same degree. All right, let's do one more and then we'll talk about one other thing. All right, so for the next one, let's look at the degrees of the numerator and the degree of the denominator. What do you guys notice? The numerator is less than the denominator. All right, so that's the second situation. So when that happens, the horizontal asymptote is the line y equals 0. Okay. Now there is another asymptote we're talking about today. There's 2 other types of asymptotes. What we're about to talk about is called a slant asymptote, and then there's also a vertical asymptote. So for the slant asymptote, it's very, very rare. Like it has to be a very specific thing that happens. So if the degree of the numerator is exactly one more than the degree of the denominator, there is a slant asymptote. So the numerator is exactly 1 more than the denominator. So could there be a slant asymptote in this purple situation right here? No. What about this green situation right here? No. The only time there could be a slant asymptote is when there is no horizontal asymptote. You cannot have both slant and horizontal. You can have neither on both of them. But if there is a horizontal asymptote, there automatically is no slant asymptote. You don't even have to think about it. You can just go ahead and say no. All right. So to find the slant asymptote, what you're going to do is to divide the numerator by the denominator and ignore the remainder. And that's going to give you the equation of the slant asymptote. Right? And then the other thing we're finding today is the Y-intercept. And I think you already know how to do this. So what do you think you plug into what? 0 into all the x's. That is always how you find a y-intercept. The x is 0. Or you're going to find f of 0. That is not different than all the other stuff we've ever done for functions. Okay, so I'm going to go back on number 1, the ones that we've done, and find the slant asymptote if there's one, and the y-intercept if there's one, and then C will do everything. Okay, so on A, we already figured out the horizontal asymptote was 3/2. So can there be a slant asymptote? No. Because the numerator's degree has to be greater than the denominator's, and that's what happens where there is no horizontal asymptote. All right, and then for the y-intercept, we are going to find f of 0. All right, so in the numerator, if I make all of those x's 0, what do you have left? 2. All right, what about the denominator? If you make all the x's 0, 0. So we get 2 divided by 0, which is a weird situation. So what do you think that means for your y-intercept? Because 2 divided by 0 is undefined. That doesn't have a value. So what do you think that means about the y-intercept? It's 1? It's 0? There is not one. We would just say none. If it's something that's undefined, it means basically that it doesn't exist. All right, so is B going to have a slant asymptote? No. Let's check and see if it has a y-intercept. All right, so this one is called G. So we're going to find G of 0 by putting 0 in for all the x's in the numerator and getting 1. And then the denominator will get 2. So that's going to make our y-intercept the point 0, 1/2. We're going to do everything on C. We're going to start with the horizontal asymptotes. So we are going to look at the degree. The degree of the numerator is 2. The degree of the denominator is 1. So the numerator is greater than denominator. So what does that mean for the horizontal asymptote? There's not one. All right, so anytime there's not a horizontal asymptote, it's possible there is a slant. There doesn't have to be a slant. For there to be a slant, the numerator's degree has to be exactly 1 more than the denominator. Is that what we have here? Yes, so there is a slant. So we're going to divide the numerator by the denominator. So if we're dividing by x minus 2, can we do synthetic division? Yes. So I would recommend that you do synthetic division when you can. If you can't, you'll have to do long division. And if you like long division, it will always work. Do I need to fill in any zeros? No. All right. So what we wrote earlier with that bullet said divide the numerator by the denominator and ignore the remainder. So in this case, the remainder doesn't matter. We're not going to use it in our slant asymptote. And so it's going to be the equation of a slanted line. So it's y equals, and then this number is the coefficient for x. So 1x or just x. And then this is added at the end plus 5. So that's your slant asymptote. So on functions that have a slant asymptote, they don't level off at a certain number. They're going to just keep increasing or keep decreasing depending on where the slant is. So they're very different. All right, does everyone understand where this came from? Whoops. This last class, I had a couple that had no idea. They just came from right here. All right, let's do the y-intercept. All right, this one is called y, so we can call it y of 0. That's fine. So we put 0 in the numerator, we get 2. 0 in the denominator, we get -2. So So that's going to be the point 0, negative 1. Okay. And then for 2, like one of the reasons why I really like rational functions is because there's a lot of like, I guess, biology-based applications to them that are kind of interesting to me. So for 2, a rare species of insect was discovered in the Amazon rainforest. To protect the species from extinction, entomologists transferred a certain number of insects to a protected area. The population P of the new colony, T days after the transfer, is given by that rational function. And then A asks us to find the Y-intercept and interpret it in the context of the problem. So what we'll do for the Y-intercept, just like all the others, we're going to put 0 in for T. All right, so we end up with 50 over 2, or 25. So what is this 25? Our two things it could be is some kind of time or some kind of population of insects. Which is it? Population of insects when? At the beginning. Very good. So I worded it differently than you guys might, but I said it's the initial population of insects the day of the transfer, or before it was transferred, whatever. At time 0. You could say the population of the insects at time 0 days. Okay. And then for B, after how many days will the insect population reach 100? So this is kind of like that one we did earlier with the 5%. We wanted to find when the drug was effective. So we want the population to be 100. So we set the population equal to 100 and solve it for T. Now I am going to go ahead and distribute that 50 because it's kind of hard to work with it the way it's written right now. Okay, so I will multiply these two together. And then 100 times 0.01, or 100 times 100th, is just going to be 1, or 1t. Where did I get the 200? 100 times 2. So I'm multiplying 100 times 2 and 100 times. Okay, and then I'll get my t's on one side and all my numbers on the other side. Now this doesn't divide evenly, but in the calculator, I got 6.25 plus 2. And it tells you it's days, so 6.25 days for the population to reach 100. So from 25 insects to 100 insects, 6.25 days. Right. And then for C, explain what will happen to the insect population after many, many years. So out of the things we've talked about today, horizontal asymptote, slant asymptote, and the Y-intercept, which of these do you think this is asking you to find? Well, this one doesn't have a slant asymptote. So horizontal asymptote or Y-intercept, what do y'all think? Horizontal. So after many, many years, it's what's happening like really, really far to the right of the graph. Let's ask it, or many, many days. That's going to be the horizontal asymptote. All right, and to find that, you compare the degree of the numerator to the degree of the denominator. So I'm going to write it in the form, a better form, where the 50 is distributed. So what do you guys notice about the degrees? They're both 1. So I need to take even though this is written in an opposite order, the leading coefficient is going to be the number in front of the variable with the largest exponent. So it's technically 25 divided by 0.01. And I don't know if it has something to do with the way biologists write this equation, but these like insect species or deer population almost always are written that way. So y equals 2,500 is the horizontal asymptote. So we're going to explain what that 2,500 means. So after many, many days, the population will stabilize at 2,500 or will level out at 2,500 insects. So I'm going to say the population will level off at 2,500 insects. So in your biology classes, did you guys learn about carrying capacity? You must not learn that anymore. My students, every time I would do this problem, they would just blurt out carrying capacity. Like they would remember that from biology, but I guess you don't use that anymore. But basically, once the population gets so big, the environment can only support so many animals or insects or whatever, and so it will level off based on how much food is available in that area.
All I remember is ATP. The only thing she said.
Okay, so I'm going to give you guys your worksheet. Let me quit